basically we deal with the networking layer of the computer network, software-defined network, internet protocol processing network. This is my whole presentation of it. So, coming to the background, as we know that the users of the internet, as always, the smart devices are growing rapidly worldwide. That's why the existing IP before network, IP basic address, which consists of only 32 bits, is not sufficient, and it is already adjusted. That is already announced by Internet Arnoma Hotal. So the option is we have to move to 128 bits IP%6. So beside this, existing IP4 networking system has several issues, including the address shortage with flexibility, lacking flexibility, reliability, and scalability at all. So the another part of this resource is the software-defined network. This is the another emerging networking paradigm in the networking world that basically deals with the management and control of the networking infrastructures, dealing with like a data center network, ISP and telecommunications network. So SDN and IPv6 jointly we introduced it as a software-defined IPv6 network. Then the thing is why the world is still not completely migrated to IPv6 network. Then SDN is just the emerging part. It's on the way of research and development for the migration. But the thing is like for every ISPs or enterprises or organizations, you can see that the migration cost, there is a heavy investment cost. We lack of skilled human resources to operate the like IPv6 network or SDN network still. Effective plan, lack of plan policy, lack of customer demand, so many. That means these are the major factors that the migrations to next generations such kinds of network is delaying. So, continuing the introduction, the current network of this world, I mean ISP or telcos or whatever network is like IPv4 and then a legacy network, we call it. Management of this network is legacy, we call it as a vertically integrated network. Then the future one is the IPv6 and software-defined network. That's why these two paradigm is on the resource and then migration process. So basically IPv6 deal with addressing part here. Routing and addressing part. Then software-defined network basically deal with the management of this, like controlling of the data plane, because it segregates the data plane with the control plane. That is completely different from the legacy IPv6 router switches we talk about. And then SDN also enables for the running of the several networking or other applications as a interfacing with these upper layer applications, so that based on that we can layer-wise network operation layer and then service layer, in the sense we have to have so many cyber physical systems, IoT or wireless sensing network. So the future networking infrastructure fully IPv6 operable and controlled and then managed by this SDN controller is recognized as software-defined IPv6 network. We introduce it as a SODIP6 network. So the problem is, as I already told about, legacy networking system has a major issues of address shortage, complex management, control operations, lack of flexibility, and still it has a greater energy waste problem. So these all had to be avoided with the existing with the new IPv6 networking and then SDN. So basically dealing with the service provider of the developing nations like Nepal, these are categorized as tier 3 ISPs, which directly provides the services to the clients and receive the, they get the internet bandwidth, purchase internet bandwidth from the other international transit providers in the ISP hierarchical network. Basically, we mean like tier 2 or tier 1 ISPs. So in the case of developing nations, the sustainability is a major issue. That means the cost of migrations, because it is not possible to migrate the networking switches, routers, or infrastructure at all at a time. It takes so many time because of the budget and the human resources. This is the main cause. So a proper migration plan in terms of available budget, network, interconnectivity, customer demand, traffic engineering is realized for the smooth transitions. We consider migration as an evolutionary process. In these articles, we just propose some kinds of like migration from existing to next generation network is a evolution one that is supposed to be as a Moran's birth-death process where the old networking system is dead and then we emerge with a new latest networking systems in the final populations. So this is basically the state of the art, like for the IPv6 and SDN. So IPv6 network migration, there are so many approaches and detailed approaches already developed and implementing. One is tunneling in the road, dual stack, and translation. Tunnel in the sense if you have only IPv4 network in between the IPv6 network, you have to tunnel the IPv6 traffic in between. And dual stack in the sense your devices or computer or any networking device is now operable both with the IPv4 and IPv6. These days, all the network equipment comes with this capability also. Then translation means you have to, because IPv4 and IPv6 traffic are not, backward compatible. That means the headers fields are different. That's why this approach simply translates the headers and all fields from IPv6 and vice versa. So another part in software-defined network, the migrations approach are defined like legacy to greenfield. That means complete replacement of the current network with the SDN-enabled network. This is in fact not possible because of the migrations we have to do in the real time. The legacy to hybrid is same like a dual stack. That means your network, now you make your existing network devices upgrade or replace so that you make it operable both with the SDN and existing legacy network systems. Another part is the mixing. That means you might have a IPv4 legacy networking enabled. Another one is SDN enabled. They interconnect. There are some of the technologies already developed, and they're on the process of research and development regarding these implementations. Particularly in my research, in case of applying the evolutionary gaming approach, we found very limited resource like one is the IPv6 migrations in the perspective of game theoretic approach. It just provides some of the migration delay, prediction of the migration delay. The other one is incremental adoption of IPv6 in terms of stakeholders, providers, and content users. So yes, coming to the two technologies, because they are underlying network layer technologies. What we concern is like if your existing network is now it's not migrated to IPv6 and then not migrated to SDN at all, then you have to think joint now because these are the two emerging network come around us. So if we try to migrate at once, considering these two technologies, definitely we might have some optimization of the cost, migration cost. This is the basic philosophy with this research also. So we analyze the migration process by introducing the some adaptation factor. That means ISP have to measure some parameters based on that, then decide for the migration to both these technologies. What is the customer demand? How much it has currently? Then traffic action between the ISPs, because how they are how much traffic IPv6 they are getting, and then how much IPv4 traffic they are going out from the network. Then available human resources, budget, and cost of these migrations. These are the major parameters we consider for these simulations work of these migrations. So based on that, we just consider the worldwide tier ISP network. That is basically tier 1 ISP is a core ISP, maybe like a Sprinter or AT&T or it's a backbone core network. They have a public peering. And then the tier 2 network is the regional ISPs, and then tier 3, this is basically of our country network or end user ISP network. They have a complete kind of hierarchical communications. Another one is we also come up with the modeling of this, because this is also concerned with the cost of migration. That's why based on income and expenditures with respect to the growth standards of the ISPs and then effects of migrations, we propose some of the parameters. That means customer bandwidth, number of customers, service, dedicated service provided to the customer, everything else is a calculation for the income revenue of this ISP. Then for the outgoing part, we but the expenditure is a kind of like a bandwidth cost they provide. They have to purchase from the internet tier 2 ISPs or other transit ISP provider. Extra cost of operations management and other miscellaneous also we can consider here. This is just as an income and expenditure basis, the model of tier 3 ISPs. So in this approach, what we consider is first, you have a number of ISPs, let's say 16 ISPs, or your country like Thailand have maybe more than 20 ISPs providing services, or Nepal generally has more than 40 ISPs in Nepal. So that maybe we consider that some of the ISP network, this is a country ISP network, suppose this is already migrated to group 2 ISPs, we categorize as a SODIP 6. So these network and then ISPs are categorized as group 1 and group ISP. Group 1 is a legacy one, group 2 is supposed to be a legacy, SODIP ISP. So what we consider here is now it has to consider the customer demand and then estimation cost and incoming ITPC traffic, because once it is already transformed to group 2 ISPs, then definitely it receives ITPC traffic, right? So based on that, now you can see the pressure. It means increasing IPv6 traffic, but it's still operate with the IPv4 network. It is providing some translation techniques or dual stack or dual stack. It's not or tunneling approach till the moment. But once increasing the the traffic, then the operations cost increase. That's why now it has to decide for some kinds of migration. Let's say next it is migrated. Once it is migrated, then again the traffic to other ISPs it gets pressure at the increase. So in this way the migration process now goes on. But the ISP, not only the incoming traffic here, I come up with the some mathematical modeling here, how it calculated the adaptation parameters for the migration decision making. So first we just model that is utilities for an ISP is supposed to be profit and then cost differences. For the legacy, for software defined IPv6 network, the profit cost plus additional that is the cost due to backward, I mean SODIP network, we suppose is also able to route the IPv4 traffic and also able to operate the legacy network in this approach. Supposed to be a dual stack one. So that this is the utility for the second one. Then the major adaptation parameter we calculated is like a 3 sub adaptation parameters, aggregation of 3. One is customer demand base. This provides the customer demand base. Second one is the traffic incoming and outgoing within the ISPs. The third one is the budget, organization budget, cost, and human resource available. So in these simulations, like if we receive like previous time step, you get one value. Next time step, you get another value. Then if this received like this, that means you are getting more pressure towards migration to next generation network, storage network. So you are in the preliminary step to go to decide for the migration of your network. So based on that, now once we model that scenario, then expected PFs of group 1 and group 2, basically 2 ISPs on like this one is like based on its profit utilities because this is the N1 ISPs, IPv4 ISPs, and then X4 to 6 means they are migrated from D4 to B6. Then N2 is supposed to be already a IPv6, SODIP 6 ISPs. That's why for the SODIP 6 network, it gives the utilities like that. So again, from the evolutionary approach, we just measure the fitness value, so that for the legacy and then for the SODIP 6 network, this gives the fitness value, and then based on that adaptation parameter and fitness value, the ISP decide for the migration decision making go for. So if we think that the fitness function value is now omega is supposed to be 0, that means this is completely independent. That means the contribution to PF is no here. So and hence migration is not necessary. That's so bad. But if omega is 1, suppose fitness of both depends solely on PF. That is still also not possible. That's why the value changes from 0 to 1. We need to consider something suitable as optimum one, 0.6 or 0.7. So another way for the simulation purpose, we just represent the utilities in terms of the logarithmic one is a convex optimization approach. This gives this utility value. So this table gives the simulation parameter we design. We assume that based on that some of the values are we consider from the references also, and then some of the parameters we consider from the taking the some survey and analysis from the Nepalese ISP, international service providers, so that initially we consider 16 ISPs in the hierarchical network, and then we just try to increase or decrease the rate of the customer demand. You can see the traffic incoming and then outgoing IPv6, IPv4 traffic, and then the organization budget and the cost. We just go for this is the way we just try to simulate with the different values. So based on that, we consider that the migration process takes over 6 years in overall 24 time step. That means every 3 months, ISP go for the calculation of his adaptation parameters and see the values. So every first 3 months, second 3 months, second 3 months like this. So ultimately, up to the 24 months, they go to for the migrations. That is based on the customer part. So increasing value to 1%, decreasing the customer demand by -2%. Increasing the customer demand by 1%, decreasing the number of customers by 2%. This gives this. So this is all about the graph shows that. Based on that, you can see. Now, if you see the sigma C 8 to 1 and then -2, that will decreasing and increasing. This graph shows that maybe at these situations the ISP is more sensitive to it's required to migrate the storage network. So this is the aggregated one. This is individual swap parameter. Then this is graph shows the aggregated one. So the adaptation value at customer demand increasing, decreasing, and then incoming, outgoing traffic, and then human resource budget based on that gives the result. So in these situations, if we see that green, that means 3 -3, 5 -2, 5 0 2, that kinds of the swap adaptation parameters raise steeply in a high manner. That's why in these situations the ISP had to go for the decision for the migrations. So for the utility analysis based on the provided mathematical model, at the beginning we consider that 50-50, let's say 8 ISPs already migrated to storage network and 8 ISPs in the ISP network had an IPv4 network. So based on that calculations, whenever the one ISP migrate from storage to IPv4 legacy to storage network, that means this now reduce. That means legacy reduced to 1 by 1, and then storage increased by 1. So in this situation, the utilities for this second group of ISPs increases, and then ultimately the whole ISPs who transfer to IPv6 storage network comes into the zero utilities. That means all ISPs are supposed to be migrated. So this scenario is only for the 12 legacy IPv4 storage IPv4 network, and then initially 4 storage networks. I think this is not much differences. We just play with the different initial value in the simulations. Okay, now in the conclusions, that means we generally focus we consider the developing nations, but going through the worldwide part also, there is still the complete IPv6 migrations and then complete SDN migration is not still is worldwide is now more than I think only 1% worldwide traffic, and then ISPs are transformed to IPv6 network. Basically, Japanese ISPs, they are already migrated to IPv6 operations. But regarding the SDN is still in the resource, because SDN implementation in the data center is almost established, but in the telecom and the ISP network it is still in the early phase. That's why we consider the tier 3 ISPs, and based on that with the different parameters, demands, interconnections, traffic engineering approach, we just simulate the scenario and then try to find out the suitable positions. That means at which position that ISPs can go for the decision so that they could have optimal migration cost. That's it. These are the references. Thank you very much.
Any question from the audience? Nope. I have not a question, but more like a opinion.
Yeah.
Do you think IPv6 will be enough? Do you think IPv6 addresses will be enough, like with IoT and edge computing around?
That means it has 128 bits. That means if you see that 2 rise power 120 is more than astronomical. So that
but IoT, do you think of sensor having its own addresses and then you deploy like 10,000 at the same time? Like that?
Based on that literature, you know that you can provide unique IPv6 address to every atom of this orb. That's like, why I think.
Do we need IPv8 soon enough?
IPv8 or IPv9, if we think that like if we have same the people's living beings in the other planets, and then we have communications, then we have to think in these situations we have to go for IPv8, 9 or like things maybe. But I think for the next millions of trillions of years, IPv6 is sufficient based on the literature.
All right. If there's nothing else, then thank you.